Hi everyone, welcome to today's webinar. This is Spencer Lee with Adapt Software. I'll be conducting the webinar today, and just a couple of announcements. We will be recording the webinar for replay on youtube.com/adapt support. There was another webinar similar to this last week, so for any of you that may want to go back and review that, it's essentially the same material as today. Next week, there will be a webinar on two-way flat slabs with post-tensioning. So that one may be of interest as well. Today, we're going to cover mainly just reinforced concrete two-way slabs in Adapt Builder. And if you have any questions, I'll save about 5 to 10 minutes towards the end of today's training or webinar for questions. You can go ahead and ask them. Should be a question queue in the GoToMeeting or GoToWebinar panel that you have on your side, and you can ask those questions and I'll try to get to them towards the end of the training. So this will be a fairly basic training for those of you who may be new to the program. I think you'll find it informative. For those that may have more experience in the program, it may be more of what you've learned over the years or months of using the software. So we're going to focus again on two-way reinforced concrete gravity floors, mainly two-way slabs. We'll talk a little bit about modeling. How do we create a model? Today we're going to actually create from a Revit file. We'll also be looking at load cases, combinations. I'm going to give a brief example of skip loading. How does that work in the software? We'll talk briefly about design assumptions, criteria, and then we're going to get into kind of the meat of being able to design a two-way slab in Builder. That will be mainly design strip creation or generation, modeling column and middle strips. A lot of that is just very subjective to the user, their tastes. Maybe you have used other software that you've had success in generating design strips, but we'll talk then about meshing and analysis, and then we'll go through some of the results like punching shear, deflections, section actions, what's the difference between designing sections versus investigating, and then also looking at the reinforcement outcome for the design sections. And then finally, we'll show, again, just very briefly, how to export back to Revit and setting a file to export back to DWG. So a lot of this material is actually covered on tutorial videos that we offer, again, at youtube.com/adapt support. So you can always go there for references if you get lost, or if you just need a refresher on one of these topics. Most of these topics are covered in separate videos in that YouTube channel. So let's go ahead. Today we're going to start out with this Revit model. This is actually the Revit. It's similar to the model that we use as a general tutorial for the software. I've modified the bottom slab somewhat to add some beams, so we can talk about how to handle beams that are mixed with a two-way or even a one-way slab. So we're going to take this file and we're going to export this from Revit to Builder. I won't go through the nuts and bolts of the Revit export. We have a video that kind of touches on that, but just a few very quick basic things that have to happen in your Revit file. They have to be the components that can be transferred to Builder must be set as a concrete material. In other words, this column shouldn't be set as glazing or as sand or some other material other than concrete. You should have components that are structurally enabled here or analytically enabled, and then also if you have components that are belonging to a foundation class or a foundation family, like grade beams, piles, pile caps, slabs on ground, those types of components, we don't read those and write them into our exchange format, which is called IMP format. So those would have to be classified almost in tricking the link as regular floors, for example, or instead of using a pile, maybe it's a column. So those are a couple of things you want to watch out for in exporting to Revit. There's more information I could send you on do's and don'ts with Revit that if you're interested, you can send me an email to support@adaptsoft.com, and I'd be happy to send you some additional information. So I'll go ahead and export this file. We're going to go ahead and just use the default column parameters. This will list the levels that we'll export, the component count, cases and combinations. This is a pretty simple model, so I'm actually going to select my combos and dump those out of this box here and place them back to not exported. We'll build everything natively inside of Builder. So let's go ahead and I'll export this information. We're going to create a file here, which is called the IMP file. We use this same file format to exchange data with other programs. ETABS, for example, Tekla Structural Designer. Many of you may have heard, if not, Adapt is actually merging with RISA, so that may be news to some of you right now, but that's going to happen May 1st. And initially, when that happens, we will likely use this format to actually just kind of close a gap between RISA models and Adapt models, being able to exchange data from that standpoint. So that this IMP format could also be manipulated manually. So if you wanted to build a file through writing this text format, you could. It's somewhat more of a long way to do this, or it could be painstaking, but I think it's formatted nicely to where if you wanted the manual, we could also provide you with a manual to write data to actually build the model from this format. So let's go ahead and call this M2. I'll just minimize Revit. I'll go over here and we're going to open Adapt Builder. And in Builder, I'm going to be using mainly today Floor Pro. I'll turn on Edge, but we're not going to be analyzing a multi-story frame, so we really don't need Edge technically. We want to turn on only RC, so this PTRC would be applicable if you wanted to model tendons, and then we're going to be using US units today. So we'll go ahead and launch Builder, and I'm going to use the file import option. We'll import that IMP file that we just created, and this will be called M2. And you can see inside of the import options dialog, now we have some more options to filter information if we don't want that in this model. So if I didn't want to create a brand new model with everything, I could just filter out the levels. You can see levels ground through 7. If I wanted to do an individual level, then the components become selectable, or you could deselect a group of components that you don't want, excuse me, to import into that file. So this might be a way to update existing levels within Builder. One thing to be careful of is that there's no auto synchronization, so the program doesn't find and replace components that might be at the same geometric location. It will literally just write this data into the new file or into an existing file. And if you have duplicate components, the program will flag those when you go to mesh or when you go to analyze the structure. So you may have to do some manual house cleaning, if you will, with the model and delete components and then import to a specific level. In today's example, we're going to mainly be using a brand new level. So we're going to create a level for everything. That means that all of this becomes unselectable. Obviously, if we're going to import everything, we don't need to select anything. And load cases, loads, and combinations, these are blank just simply because we didn't have any of that information from Revit. Now, if you were importing from a program like ETABS, you potentially could import reactions from ETABS into Builder, depending on the type. Gravity reactions almost always, but lateral reactions depending on the type of analysis it comes from in ETABS. That's that is dependent on what you want to do inside of Builder. So we're going to leave those blank, and we'll go ahead and say okay. And now you can see we're working inside of Builder. So I'm going to just navigate down in single level to the level we're going to be working in mainly. We'll be working mainly at level 1. You can see this has a few variations. There's nothing super complex. One thing to note is there's quite a few beams in this model. So we're going to talk about how do we handle these beams kind of on the perimeter in conjunction with handling the slabs. let me go back over to this file. So we've talked a little bit about how we're going to build the model. The model is really built. We just need to add some loads and load cases, combos, and skip loading. So let's go ahead and add some gravity loads to this model. I'm going to go over here to model, or excuse me, to loading. And there's a couple of ways to do this. We could add a patch load by just selecting points, creating a polygon, assigning a load case and a magnitude to that load. The load cases are listed here under load cases. There's a couple of reserved load cases, one being dead load, one live load. This is really superimposed dead load. Self-weight is automatically considered. So this, we're mainly going to be working in this realm here, this type of a realm. This building loads, we're not going to talk about until we get to our lateral multi-level webinar. This is reserved for wind forces and seismic forces applied to a multi-story frame that would be in reality it would be applied when the building is in service, let's say. Understanding there could be construction loads that have to be considered for lateral, but this is mainly for an in-service condition where you have the full frame in effect considered. So we'll be working mainly here in general loads. So we'll use just the reserved cases here, dead and live. This live load case is currently this is set to being unreduced. This is non-reduced or unreduced live load. Now, there's a little bit of confusion. I think that's why I want to touch on the skip loading feature in the program. If you say, well, this live load, I want it to be reducible. And you say, okay, let's reduce that live load. In reality, if I come back and I say, well, I'm going to add a patch load, and we'll just put this patch load over everything. There's my live load. And we'll say that live load is going to be, I'll just say it's going to be 50 PSF. And we said in the load case dialog, that load is reducible. That's true. However, the reduction tag in that dialog, this reduction tag here, is only applicable to columns. And there's two cases where it's applicable. One is when you design columns. If you use our load takedown feature, which is a way to accumulate loads based on tributary. Let me go back to multi-story for a moment. So if I use the load takedown feature here and I run load takedown, we'll calculate those loads, and you can see that the program has created these tributary boundaries. I'll try to outline one for you so you can see that. There's a tributary boundary there. And this tributary boundary gets calculated for each vertical component, walls or columns. Program calculates the area. I'll call this area just A1 and this one A2. And as you move down the bottom, it accumulates that, based on the load takedown function. And so when we design these columns, we could design those columns either from an FEM solution, which would be based on running this analytically through, we'd have to mesh the model and then run the finite element solution for it, or based on the tributary takedown. I'll call this trib. I can't really write with this, but, and either of these could be, either of these options, let's say, produce some set of reactions. So there's reaction from FEM, there's reaction from tributary, I'll call R1 and R2. We'll assume that that reaction is only for live load. Well, once you get into column design, you can say, do you want to reduce that reaction for the live load when you design the columns? Or another option where live load reduction is used is if you want to apply when you have, for example, a transfer condition and you want to apply reactions from a column stack above on a transfer, then you have the option to reduce live load here also. So when I rerun a single level and I include load takedown or lateral reactions, I can also include to reduce the live load there. Those are the two conditions where you have the ability to reduce the live load when you use that tag in the load case dialog. I was going to mention the other one. If you go to column design settings, you'll notice here it says live load reduction. Yes. All that does is that says, okay, for any of the live loads included in the group of combinations that you're designing columns for, make sure when we write that reaction into S concrete, you reduce the live load. So those are the two conditions where it applies. So it doesn't really apply to floors when you use that option. Hopefully that's something that those of you who have used it have been able to learn just through our documentation and through support and maybe other videos. But where you can reduce floor live load is we've already added live load. We added 50 to this. I'm actually going to go back and add dead load. So let me do that really quick. We'll go back here. And in this case, I'm going to select the slab. And I'll select this slab. And we're going to use the patch load wizard. So this just maps the load to the selected slabs. We'll say this is 20 PSF. And then also this balcony I'm going to assume has 100 PSF live load. I've already added 50. The loading is always cumulative in the program. So we're going to go and I'm going to map an additional 50 live load here to the balcony just to show that procedure. So now we have the following loads. We have the dead load of 20, we have this live load of 50, and I could go over here to the visibility panel for, excuse me, for loading, and we'll go ahead to patch load. Let's see, patch load and turn on the dimensions. And I'm actually going to reduce the symbol size maybe by 1/3, and we'll go back and show those loads. So we have our 50 right here. We have our other 50 there. That's 100 cumulative. And then our 20 again mapped to the outer slab region. So that's the loading on the floor. If we wanted to reduce live load for the floor, other than just assigning a set of loads that actually is already reduced, that's kind of the manual way of doing things, we'll call it. We could do the following, and this shows the example of skip loading. So I'll go back here to subregions, and I'm going to create multiple regions in the slab. I could draw polygons. I can draw dividing lines is really what I'm going to do. So I'm going to click a point and I'll go through and click another point. And then in this case, we'll do this region here. And I'll actually do a region there. So you'll notice once I could bend this line. You can create, it doesn't have to be orthogonal. You can bend it and I could snap on certain points with it. Okay, so these are going to be my my sub-regions, which also can be used to skip live load. So if I go to load patterns now, you can see the program adds these, let me see if I can find my pen here. It adds these little handles, these blue handles, and those blue handles allow you to select those sub-regions. These regions are used to really skip load. But when I talk about this in the context of patterning, I can reduce live load. So I'm saying that I want to set my live load as the pattern, the load that I want to pattern. I want to reduce that load wherever it's applicable when I set up a pattern. So the first pattern, for example, would be everything. I'm just literally going to select all of the regions. There's pattern 1. Pattern 2, let's say, is going to be something, if you really wanted to skip loading, this might be pattern 2. Pattern, let's say 3. And then pattern, pattern 4 and so on. So you could set up any number of load patterns. There's 4 there. There's pattern 1, 2, 3, 4. In this case, we might only use 1. This again would calculate the reduction factors for each region. If I select OK, you'll notice it actually shows the reduction factor for that region. And this is based, I believe, on IBC, the alternate reduction method. It's either in IBC or ASC 7. I can't recall. We're already we're set to ACI 14, IBC 15. So I believe it's IBC 15 methodology for the calculation of this. But these reduction factors are then used when we solve the combinations for pattern 1. So making a segue in here into the combinations, you can see that the combinations set up by default are just some basic gravity only combos. So we have a couple of service combinations and strength. As the user, if you have multiple combinations you want to enter here, that's something that currently you would be able to set up as a template. So if you write the combinations in, you can always save a model as a template. My recommendation would be, if you do that, just set up your combinations and your loading first in the model with the the model in place. Go back to save as template, and then this would save criteria, material, or combinations. It saves it as an APT file. That could be placed anywhere, and then you could go back and use that file over and over when you create a new model. So that allows you to select the template. Okay, so you'll notice here we have pattern 1. Let me go back and expand that. We have patterns 1, 2, 3, and 4. So if we wanted to include pattern 1 into our combos, I might, instead of using live load, I might want to use the reduce live load, which might be this pattern 1. And here I might say, well, that needs to be, here 0.3. So if your goal really is just not really worrying about skipping, but you want a pattern load, then you would set up the subregions how you'd like them, and then replace the factors from the live load to pattern 1 in this dialog. Now we're not going to use patterns in this example. I just wanted to show how that works. We're going to just use full live load. So I'll go back and just delete out those subregions. Let me go ahead and save the model. Okay, and then you'll notice if we come back over to load patterns, everything's gone. We just deleted them. This window here removes the patterns. Everything is set back to live load. Now in this dialog, we'll talk a little bit about the combination types. So we have different analysis and design options that are set to each combination. Service sustain, service total, strength, crack deflection, no code check, long-term, and then P delta. P delta we're going to ignore. We're not analyzing a multi-story frame. So talking about how does the program, what does it do with these types of combinations? Well, for service and sustain, I think that for service total and service sustain, that's more in the context of maybe a post-tensioned slab. However, I think it can be still used as, in conjunction with RC methodology. So when we talk about reinforcement for these two combination types, the program is really calculating minimum reinforcement for whatever criteria you have set for your design strip. So if you've set a two-way criteria for a design strip and there's no post-tensioning in the model, it becomes two-way RC. And therefore, for two-way RC slabs, we check minimum temperature and shrinkage reinforcement. So for these two combination types, for an RC slab, they would actually yield the same amount of reinforcement because it's not dependent on the moment, it's not dependent on the stress level, it's just dependent on the area of steel and the grade of, or the area of the section and the grade of the reinforcement. So these two would yield minimum temperature shrinkage reinforcement. Strength would actually be calculated based on the moment demand and any axial demand in a section. So if your ultimate moment is 100 kip feet and the program, if the user doesn't enter any base reinforcement, then the program would add enough rebar to meet that demand of 100 kip feet. So that's how strength is handled in terms of reinforcement. Crack deflection, we don't calculate reinforcement for crack deflection. It's just a way for the program to produce a result and check the slab for cracking. So it's dependent on the slab being analyzed, and it's also dependent on the design cuts or the design strips being calculated or investigated in order to produce that result. We have to know what reinforcement is in the slab before we solve crack deflection. And that actual option is under analysis. So you see it's grayed out until we analyze and then design or investigate the sections, then we can check crack deflection. So if you wanted to check cracking for an existing slab, you would model this. I would go in and I would draw in, reinforcement, or maybe put a mesh, around the extents of the slab. And then I would investigate. Investigate just means the program checks capacity. It doesn't add any additional rebar, even if the capacity is not met or the demand moments are not met. So this is a way to check cracking for existing slabs. I'll talk a little bit about base rebar here in a moment. I just mentioned that in that example, but let's go back over here to combos. So we have cracking, no code check. You can set a combination to just don't do anything with it, just show me the result for it. So that might be most commonly used for when maybe you want to set up a combination for self-weight only, PT only, no PT in this case, but live load only, superimposed dead load. So you can kind of see and break out the behavior based on each individual combination. Long-term deflection is a way to combine the results from multiple combinations. So for example, and then P delta, we're going to ignore that. So if I set up a combination here, I'll just go to cracked and I'll say, okay, I want to know what the cracking is under sustained. So I'll call this sustained CR. And I'm going to actually make this equal to the sustained service. The only difference is this is not calculated for rebar. It's used to check cracking or crack deflection. This is used to check for minimum reinforcement primarily. For PT slabs, this is used for more than that. It's used to check stresses and so on in the slab. But we'll go ahead here and set this up. We'll say there's 0.3. And then we're going to add another combination called long-term. This is, again, just a very simple example. So long-term, I'll say, for this example, the creep factor, we're going to just assume is 2. And or maybe it's 1.5. It depends on what the user applies for the creep and shrinkage factor. We'll say it's 2, and we know that the long-term deflection is going to equal the creep plus the instantaneous deflection, let's say due to sustained loads. We'll say that this is going to be 3 times. This will be 3 times sustained CR. This combination here. I think I'm referencing the wrong combo. Let's do that. Okay, so long-term is 3 times sustained. So again, you could build out multiple combinations and reference other combinations inside of these long-term combos. All right, so that's a brief overview of the combinations. Let me come back to this document here. We talked about skip loading, combos, cases, and loads. Design assumptions and criteria. So I'll come back over here to criteria under concrete. The concrete is pretty straightforward. I think you can model multiple materials here. We're going to just assume concrete 1, which is 4,000 psi. There's also an option here if you wanted to add steel fiber. This is proprietary to Dramix, which is a product by the company Beckert. You could actually add a concrete material that includes some dosage of steel fiber. So we could say, well, this is an elevated slab. I want to include this particular type of steel fiber, and I want to specify a dosage. There's some other parameters here that would then take into consideration that that dosage of steel fiber into your slab. So theoretically, you would have less rebar required. Your punching shear capacity would increase. These are all based on the properties of that fiber inside of a concrete matrix. So that's what that's for. We're going to go ahead and delete that. We're going to use just basic plain concrete. And for rebar, we can specify rebar material. This really just takes you back to this dialog. It's just more direct from an icon standpoint. Design code, we're going to go ahead and use ACI 14. And we can, in Adapt Builder or Floor Pro RC, we can report crack width. So if we wanted to report how, what the crack growth is, we could report that. This is actually different. Obviously, it stems from, it stems from just general cracking of the slab, but this is a different check than the crack deflection check. They're similar, but you actually produce results differently between the two. So I'll show you that. If you wanted to limit the crack width, you have the option to limit crack width. The program specifies, or you specify the limitation in terms of the width of the crack. And then this help menu, if you look at that, that actually shows that we use European code methodology for the crack width calculation, or for the cracking rebar, I'll call it. So we're gonna report the crack width. We just won't limit the crack width. We'll report it though. And you have additional options for strength reduction factors here for design code. Under analysis and design options, this really just specifies how beams are considered. This regular floor system versus waffle and joist. This is kind of nuanced, but it's really important. If you have this set to regular floor system, let me come back over to the model here. You'll notice this beam is broken up into, I'll call it 1, 2, and 3 nodes. There's a node here, a node there, and a node here. So if you add a support line along this beam path, I'll color this in black here. So if I say, well, my support line is going to go from here all the way over to there. And notice I've skipped snapping on points 1, 2, or 3. When I design a cut, when I create cuts through this design strip, and I look at that cut, the cut physically looks like something like this. Well, technically, this is shifted a little bit that way, but it's a T-beam in essence, unequal flanges on either side. And when the program solves the reinforcement for this T-beam, it actually ignores the stem. So this is a way to consider the modeling of, let's say, an architectural beam, but not designing for it. And what will happen is this beam physically will draw in moment because it's stiffer than the slab, but you're just not designing for that moment. The slab is taking, the brunt of that work in terms of a design capacity. So if you want this beam to be considered as part of the structural element, the structural member, then you would have to snap on these points. I would have to snap point 1, then point 2, point 3, point 4. Technically, you only have to do 1 per beam segment. So that can be, if you're a new user to this, you don't know that can obviously cause issues. So if you have beams in any of your models that are structural, I always recommend to use this option, include waffle/joist construction. That just means if a design cut cuts through a beam, regardless of how your support lines are laid out, it will always include the beam stem as part of the physical section that will structurally, resist the bending and so on. So this is what this means here. There's a few other options here. I'm not going to go through all of them, but we have a document. Let me point to this. There's a document over here under documentation, and the documentation option is shown right here, design options. This kind of defines all of these options in detail. So the main thing that I wanted to point out in that particular location was right here, this support option. So for single level mode, this is the support condition that we're assuming. We're assuming a fixed roller by default. You could change that to anything that you want. If you want it to be fixed, or maybe pinned. If you want it to be pinned, then I would release, rotation here. Now it's pinned. So be aware that by default, as a user, you should come here and check, well, what support conditions do I want for this model? And if it's something different than what we default to, then you need to change it here. You can include twisting moment design per the wood armor method for two-way slabs if you'd like through this option. And then let's say you add base reinforcement. This tells the program, consider minimum reinforcement. Do you want the program to design the minimum reinforcement? Yes or no? If you add base reinforcement as a user, and let's say I come here and say I want to model some reinforcement in this slab. So we'll go over here to rebar. I want to model rebar mesh. And now we're going to say I want this to be, number 5s at 12 inches on center, top and bottom. My cover is shown here. I'll go ahead and create that. And after I create that, now this is just symbolic of where the mesh is. You can actually go to visibility render and you can see there's a mesh shown in there. There's the slab with the 2 layers of rebar in the slab. So that covers the entire slab in this case. You could also, just draw that in. You could go back and instead of using the wizard, say, well, I only really have a mesh here, and then go in and specify its properties. But however you add the base reinforcement, it can be through mesh, it can be through banded. Maybe I want top bars. I know we have top bars over our columns, so I'll change that to 4, top bars. Right now they're shown as grouped. They're just lumped together, but maybe I want them distributed 3 feet on either side. So now we can change how those are distributed. Once you do that, you could graphically change the distribution. You're not limited to entering it in a table. That changes the distribution and so on. So that's banded. We call that banded reinforcement. This is all generally classified as user defined or base reinforcement. And then distributed reinforcement, we would go ahead and define the bar and then the range. So from point A over to point B. By default, we only show 2 bars in that range. We could change that. Maybe I say, well, I want the spacing to be fixed at 12 inches. Calculate the number of bars, and it calculates 121 bars in that zone from point A to point B. So that's how the base reinforcement is considered. And coming back over to this, just to kind of close that gap, if you add enough rebar in a bottom or top mat to meet the requirements for temperature shrinkage, then I would just turn this off. There's no need to have this on. If you've already added it, technically the program wouldn't add it for that particular purpose. It might add additional rebar if it doesn't meet, if the calculated amount of rebar doesn't meet spacing requirements. So let's keep going here. For shear design, there's options here for punching shear. I won't go through these all in detail. We're running, starting to run into a time crunch, but I won't go through all those in detail. I would just go through the documentation, or again, we have a video related specifically to punching shear. We're just going to leave these settings as they are. Rebar cover, you can set the cover for your criteria types, 2-way slab, 1-way slab, or beam. And that is measured from if you have a slab, and let's say this is X direction, so corresponding with this, we have our outer layer and our inner layer, and your support lines will dictate what's the outer and inner. Well, the cover here is actually to the outer layer of rebar. So this 1 inch is to here. If you want to shove everything further inboard, then that number would have to grow up, obviously, to have more cover for the bars. But this bar is called the outer layer. This bar grid is called the inner layer. And those get defined again when we define our design strips. So let's go ahead and do some of that work for design strips. So whenever we have a model like this, we have to generate strips in order to obtain just meaningful, or let's say efficient design results as it relates to reinforcement mainly. And when you get into post-tensioning, it relates further. It relates to pre-compression checks, stress checks, balance loading checks. So we're going to cover this slab in design strips in the X and Y directions. We'll do column strips, middle strips along here, and then we'll flip over and do some Y strips. So we're going to start under floor design, create X direction support lines. We can do this using our dynamic editor or through manual creation. I'm actually going to use manual creation today. So I'm just going to snap. I have a habit of snapping outside of the slab and then coming back and addressing those. So we're going to snap to each beam location. Okay, there's one, I'll call this a column strip. There's beams on it. It's a column beam strip. And then the next strip is going to be a middle strip. It kind of flows into a column strip here. So This we're gonna call a middle strip. We don't really classify them as one or the other, but let's go ahead and just come back. And now, one thing to note here, I'm actually going to stop this one and I'm going to continue it again. The reason I stop it is because there's two ways of handling beams. One way, this one, for example, this is continuous all the way through. So you basically have, you know, two-way here. You have a two-way span here, but then along here you have a beam span. So how does the program handle that? The program knows that this is going to be a beam. You know, any cut that covers a beam here will be designed as a beam. However, because this design strip, if I double click on that and look at the properties of it, the design is set to two-way slab. So while the program will calculate the required reinforcement for a beam, the minimum rebar, for example, for this span and this span are different. This is based on temperature shrinkage. This might be based on minimum flexural steel for a beam. And the program recognizes that. However, when we go in, we add the rebar to the beam, the size that it's looking for, the bar size that it's going to show is going to be based on two-way slab criteria. So under rebar, for rebar size and material, you can see that for two-way slabs, the size that it's going to use for top bars is number 5s. And I'll actually say it's number 5 and 5. For beams, it might be, you know, number 7s and 8s. So in this case, the program would say, well, for temperature shrinkage for span 1, we need 4 number 5s, but for minimum flexural reinforcement for span 2 and 3 and 4, or let's say 3, we need, you know, 6 number 5s, which might actually be, if you change this to beam criteria, you might actually only need 3 number 8s. It's just an equivalent, you know, number of bars. So be aware of that. Here we're going to directly classify this strip as a beam. If you use our wizard, let me come over here to the floor editor. This is the support line wizard. And here, if you actually click near the endpoint of each beam segment, I'm clicking multiple times because I have multiple beam segments, then what happens is the program will break this up. So there's span 1, and you can see I can adjust that. That span is two-way slab. This span is beam automatically. This is beam, and so on. This last one is beam. So the program knows where to break them up at each beam segment using that wizard. Let me continue on. Okay, so there's my next column strip. I'm going to actually change that to two-way slab. Now I can come back and adjust these if I want, these points. You can see I can just come back and snap perpendicular to the slab edge. This is more for presentation than anything. It sometimes can affect the way that the cuts are made, depending on, you know, slab reentrant corners and whatnot, but I'll do it just for sake of cleanliness. So this is our layout for mainly column strips. For middle strips, in the previous versions to 2019, there was an option to automatically create middle strips. That was removed because it was incompatible with the way that the wizard works. So we're actually going to be putting that back into the program. There's a question here. Yes, the question is, will there be a recording of this? And the answer is yes, Jackson, there will be a recording. There will be a recording of this put on our YouTube channel. Okay, so I'm now going to just go ahead and introduce some middle strips. This is just really free form. It just is required by the user to enter a design strip for the middle strip. So we're going to go back, use some of our snap tools, and I'll just go in and enter a middle strip from here over to that point. Maybe from there to there. I'll add another middle strip along this path. Okay, and I'm also going to add a splitter right here. If I take a cut through this location, you can see there's a step there. So I may not want that balcony to be included in this design cut. Whether or not you want that, if I don't want that included in the design cut, because right now if I generate my design strips, if I go back to floor design and generate sections, you can see these design cuts protrude into that balcony space. And so let's assume we don't want that to happen. So I'll just add a boundary. I'm going to put a splitter, and I'll put that splitter along this path. And now what will happen is I'm left with this. Now I don't have any strips down here because there's no support line below the splitter. So I can add another splitter if I really want to get some results along that direction of the balcony. Something like this, and then I can regenerate my strips. And you can see there are strips that enter into openings. So if I don't want strips to enter into openings, we can just go ahead and add a splitter on each face, let's say, of that opening. The program will cut that out of the tributary. So we might have something like this. Okay, that's how the strips will be laid out in the X direction. If you want the program to use the effective flange, or rather the effective properties of each beam when it designs a beam, you can go into the beam criteria under design section options. Here we have additional options. How many sections do you want per spacing or per span? What's the spacing of the strips if we use that option? Right now all of the strips are spaced at 2, or sections are spaced at 2 feet apart. So if you wanted to say, well, I want the program, when it calculates the required reinforcement and it evaluates this section cut where I have a beam, use effective flange properties. So the program would calculate the effective properties. There's 2 other options to exclude or include reinforcement outside of the flange. So if our flange is here, let's say, that's the calculated effective width, and we have some base rebar that falls out here. You can tell the program, include that base rebar as just a lump sum at some effective depth within that effective section, or discount it, don't include it. So there is that option given also. Okay, so those are the strips for this direction. We'll go ahead and turn off that direction. I'm gonna just isolate, and we'll do the Y direction now. So this direction is similar. We have really beams in both directions. I'll go over here. This I'm going to say is kind of really a middle strip might fall along this path, or it might fall here and kind of bend over. So I'll just go up to this point. Actually, no, let me come back over here. I'm going to go from this point down to this wall and just continue up this stream. Okay, I'm not using the wizard in this case. I'm just manually applying these. I'm going to go along the column strips first. So we'll do column strips, then we'll come back and do some middle strips. And for sake of time, I'm not going to pay as much attention to the classification of the strip. Normally I would go through and make sure the beams are classified as beams, but this is just kind of gives you a general guidance as to how to lay these out. Now this is a little bit unique. You know, this strip, I could go from here and then bend it up like so. I could just produce something along here and then something separate along the wall. So maybe I'll do that. Let's go to this wall, place a little strip along the wall, and then maybe start here for this column strip. Like I said, it's fairly subjective to the user how they want the strips broken out. And then we might have a middle strip, you know, along this path. So where does this middle strip end? Well, I might actually bend it here, and it might actually end up right at that beam location. So we'll make sure that those 2 points coincide. It looks like they're close. And then I'll do a couple of middle strips in addition to what I have. We'll go from this opening out to the slab edge, and then along this path here we have a beam. We'll just run that straight up like so. Okay, and we have one more, maybe over here. Okay, these are the middle strips. In this case, I'm not going to generate or trim those back. I am going to add splitters, remember, with the opening. So we'll go to the Y splitter, and these splitters will be placed where I want the program to terminate the design cut. So remember, these design cuts are mainly flowing in the X direction, perpendicular to the support line. And so we'll place the splitters in the same direction mainly as the support lines themselves. And now I'll generate the cuts, and we're left with our, let me turn the splitters off. We're left with our Y cuts now and our X cuts. Okay, those are the design cuts. We're now going to come back and we're going to mesh this. So I'm running low on time, unfortunately, but today we're just going to mesh this as is. We'll just use the default settings here. I'll mesh the slab, and we're going to analyze. So in order to obtain not only a solution for just the general FEA results, but also in order to design the strips and to go further downstream and calculate crack deflection and reinforcement, we have to obtain a general solution first. So we'll go and we'll execute the analysis for our load cases. Now I removed those patterns. Let me just select the combinations shown here. We'll go ahead and run that. Once we are done analyzing, we're going to design. We've already generated the design cuts, so we don't technically need to do that again, but I could design the cuts. So I'll design or investigate. If I investigate, remember, it just gives me results based really on capacity. What's the base capacity of the slab? Here we're going to design. What's the capacity, but also calculate the reinforcement needed to meet the requirements per the load combination types. So we're now designing the design cuts. This is really where all of the calculations come into play, where we generate the reinforcement in the slabs. So that's been done. Now, prior to that step, I could have also created a punching shear solution because that's based on the FEA results. So I'll just go back to my default display. I use this option here, and we'll go to floor design, and I'm going to execute punching shear. And you can see when I think when I run this punching shear, this is kind of grayed out down here. I'm using actually a new version for those of you who are deeply involved in the software, have used it quite a bit. You'll notice there's an option now for a property grid. So this property grid gets populated on the left-hand side, and this will be released here soon, but this allows you to control all properties for any group of selected components through the grid rather than having to double click into a property dialog. But anyway, so there's a few other changes. One of them is this thing right here for punching shear. If you don't have a strength combination selected, the program won't let you check punching. Once I come over here to check strength combination, then I'm able to check punching. So this gives me a status of the column stress ratio. You'll notice that the columns near beams are not checked. If they're connected to a beam, they won't be checked. If you really wanted to trick the program, you could actually take these two beams, I'll right click and disregard them, and then I'll just check punching again. I don't have to reanalyze, I can just check the punching again. Once I do that, it actually produces a result. So that's a way to trick the program if you want to check punching at columns near beams. Let me just set those back to consider. Okay, those are back turned on. When you disregard or consider, you essentially ignore that component when you run the analysis of the slab. But these are, there's no reinforcement required for these columns. I don't think I have a heavy enough load, but that's ultimately, you would set up your shear design requirements. We talked a little bit about that. Go through, run the punching shear. Graphically, you can check things, but that doesn't, maybe that doesn't give you enough information. You could always go to reports, and under punching shear, There's 3 different reports you can produce, including an Excel file that kind of dumps all of the numerical calculations into these results for the stress checks. So this is just a way to get information based on, this is really a reflection of what's going on behind the scenes, just in a more presentable format other than you going and digging through text files. So we've gone through, we calculated the strips. Now for design section results, we'll use the analysis tab again, but we will go over to design section. And a few of these results are more specific to PT slabs, like stresses. This is for PT, balance loading, PT. And so those 2 tabs are not, they'll just basically produce 0 on your design cuts. We're not going to use those, but you could look at deformation, for example. And the deformation tab is dependent on the span. So like, for example, this strip here gives me pretty reliable results because the span that it's using to produce this result is dependent on this point and this point. And when I went through and set the support line up, I put point, you know, I had 7 or 8 points along here. This one here is unreliable, okay? And that's because of how I set the support line up. I said that there was a point here and a point right there. So what the program is doing is it's taking the maximum deflection integrated value on any of those cut lines, and it looks to be about 0.31, and it's taking this span from 0.1 over to 0.2, which is truly not the span, dividing it by that max to get this span deflection value. So if you want more accuracy in these results, specifically for deformation on strips, make sure that in this case, I would have cut this thing, I should have really cut it into span 1 and kind of project a point along here. This might be 0.1, 2, 3, you know, 4. Here you might put another point here, 5, and then 6. And then we would have had 4 or 5 spans and had more reliable results if we're checking it in this fashion. So the code check, the green or pink code check where you see the sections, those come into play. This is being code checked against L over 360. That is set up under display, maximum span deflection 360, and you can produce that result in either direction. This is just in addition to contour results. So coming back to the actions, you can produce any action on the design strips, bending, shear, torsion, in-plane bending, and so on. So these are just mainly just strip results if you wanted to investigate kind of what's happening globally in a model along the X or Y strips. Ultimately, we might be more interested in things like investigation. What is the moment capacity of my design strips? And this shows me the capacity curves for the strips. Green is positive capacity, and the blue is negative capacity. So you can see that if I turn on moment capacity with demand, the program is going to overlay the demand envelope on top of the capacity curve. So right here, for example, where we have these gaps, this would indicate that probably the minimum reinforcement controls the demand. This is the MU envelope, this gray curve. There's quite a bit more rebar needed there, or let's say capacity there. The demand capacity ratio, for example, is 0.42, 0.38, and so on. So if I double click on that cut, I can go to design sections and see that minimum reinforcement is controlling at that location. We need 3.9 square inches over this width. And this is a nice graph. It helps kind of indicate where you have locations where there may be, you know, areas where strength is controlling, like right here, the gray is overlapped right on top of the green, or right on top of the blue rather. If I double click on that, strength will have controlled. You need 5.5 square inches of steel just to meet the demand moment of negative 259 kip feet at that location. Okay, so that's the investigation curves. You can also look at reinforcement values. So for strength, dead and live, the calculated reinforcement is shown here. This is more direct. Where do I need the most steel in this slab, and this is actually new to version. This is new to version 2019. So this shows me the required rebar for strength, for example. Clearly we can see where we have high locations of positive reinforcement versus bottom reinforcement. You could also do it based on what's provided. So if I say, well, I want to see this is required, what's the program providing? I would have to generate the rebar plan for that combination first. So here we can go and generate reinforcement for strength, dead and live. After doing that, this is the rebar outcome for strength, dead and live. Let me just turn the rebar off graphically for a moment. And then I can come back and just toggle this back. This shows me the actual rebar that's in the slab for that combination. That can be done for an individual combo or an envelope in the model. Okay, so those are just some graphical results. Ultimately, we want to know, well, what is the rebar for the slab overall, right? We'll go to rebar and we'll go to calculate the rebar, and I'll do this for an envelope, for example, or for an envelope of service, minimum reinforcement, strength, or individual combinations. This is now my reinforcement layout for the entire slab. And a couple of things here before we close. Red reinforcement indicates bottom rebar, green is top rebar. Blue means that the bar is located in an area where you have differences in thickness, or there's a change in geometry for which the bar passes through. So if I look at reinforcement, for example, on the bottom, you can see that because this bottom rebar is shown extended. Okay, this is bottom rebar. This looks a little bit weird because there's a beam here. This is bottom rebar, but it's shown extended outside of the beam width. And because of that, the program flags this. It's really just a detailing warning to the user. This bar is supposed to be in the bottom of the beam, but it's distributing outside of the beam. Therefore, flag it, indicate to the user this blue reinforcement. The reason it's doing that is this actual design strip, if we go to design, this is set up as a two-way slab. So if I change that to a beam, what it really should be in this case, and I come back and let's say redesign just that one strip, let me turn on the section cuts. I'll just redesign that strip as a beam now. It's going to update the results for that strip. Everything else will be left as they were. So now I'm a little bit out of sync with the entire model, but that's okay. Now I'll just go back and recalculate the rebar. Okay, and you can see, let me just toggle this again. This bar is changed to 8. It's in this case, it should be shown as a piece of grouped rebar. Let me make sure. Yeah, that's still shown as beam. So something's going on there, but this really should be shown as 3 number 8s by 20'6". This at 40 technically should not be there, and this should just be shown as 1 bar. So I'll have to check that out just as a matter of making sure there's what's going on there. But that's how you can make modifications to design strips and then recycle through the design of those strips. So we'll go ahead and close there today. And I'll just go ahead and open it up for any questions that anyone has. We have about five more minutes for questions. If your question cannot be answered, if you have questions outside of the meeting, what we can do is go ahead and you can send me an email or send our support team an email at support@adaptsoft.com, and I'd be happy to answer them outside of the meeting. So thank you for everyone attending today. Hopefully everyone's healthy and is safe. But if you need to go ahead and exit, please feel free to now. But if you have any questions, I'll wait for another 5 minutes or so. And for those of you that did not hear, to ask a question, there is a question box, or there should be an option to present a question in the dialog that you see, the floating panel for GoToMeeting. As a reminder, this will be posted on youtube.com/adaptsupport also. All right, looks like there are no questions unless someone's typing. I'll wait just another minute or so here. Okay, we'll go ahead and close in. Again, I appreciate everyone's attendance. If you have any questions, you can comment or question at support@adaptsoft.com. Thank you, everyone.